All right, hi guys. So 5.6 is all about exponential functions and logarithms in integrals. Okay, so let's uh, jump off here. So let's look at exponential functions first. So integral of e to the x dx. Okay, so we talked about this in 4.10. Again, this one should be very quick, right? Just because the derivative of e to the x is e to the x, so the antiderivative is e to the x as well, plus c, of course. Then for a general exponential function, remember these rules work in reverse, right? So if you know my derivative, so what's the derivative of b to the x? Okay, so that's b to the x, and you multiply it by the natural log of the base. Okay, now since we are doing antiderivatives, we divide by the natural log of the base. Okay, and plus c. All right. So let's just go through a couple examples here, getting used to it. We did a substitution example with an exponential function last time. So let's try this guy. Find the antiderivative of e to the negative x. Okay. Well, if you watched my previous my last couple minutes in 5.5, this would be a little quicker, but remember what I said about exponential functions? It's the exponent is the inside function. Okay. Um, so if you wanted, you could do u equals negative x, du equals negative 1 times dx, so negative dx. So we could move the negative to the other side because we don't have a negative, so negative du equals dx. Okay, so this becomes integral e to the u times negative du. Okay, so that negative one can be pulled out, but then e to the u, antiderivative of that is e to the u, and then we can plug back in the negative x. Okay. If you watched my previous video, or not video, excuse me, the last couple minutes in the previous video, um, right, and you internalized it, right, of course, um, we could have just jumped and we have this, and I noticed my inner function is linear. It's just a constant times x. So my antiderivative will be the antiderivative as if it wasn't there. So the antiderivative e to whatever is e to that thing. But then we divide by the derivative of the inside function, negative x. Okay, so that's negative 1. We divide by that plus c. And then that simplifies, right? Again, this only works if it's a constant times x as your inner function, or like a linear function is what I said, right? So something like ax plus b, right? So maybe it's just a constant times x. Maybe there's another constant added to it. Either way, the point is when you take the derivative, you just get a, and that's what you divide by out the front. Okay. Now, like I said at the end of last video, that's not necessary because clearly we did it with the normal route with this use substitution. Okay. But it's just, it makes things quicker once you really get the hang of things. Okay. Yeah. All right. Let's try another one. Again, we did an example with an exponential function in 5.5. Um, so go ahead and try this. Pause the video. Okay, hopefully you paused. So remember the inside function is our exponent. So we'll do u equals negative 2x cubed. Okay, so du equals negative 6x squared dx. And then we could divide by negative 6 or multiply by negative 1/6. Okay, and I get my x squared dx. So this becomes integral e to the u times negative a sixth du. So again, I can pull the negative 1/6 out, and then the antiderivative of e to the u is e to the u. And then we'll plug back in our exponent plus c. Okay, awesome. Okay, so let's do an exponent, another example here. See what's going on. We're trying to, get a lot of variety with our exponential and antiderivatives, just so we can see really what they look like, even though all of our strategies still work, but we want to get used to doing the antiderivative of exponentials. Okay, so let's try this one. Okay, this one's interesting. It has a root, so you might think you want to do that root strategy, and you'll find that it actually does work. Okay, so when I was showing you those substitution strategies where there's a root, there was like two ways to do it, the normal way, and then you let the entire root equal the substitution variable. Either will work here as well, but the important thing is noticing there's an inside function, 1 plus e to the x. Okay, so the normal way is just, oh yeah, well, u equals 1 plus e to the x, right? U equals the inside function. Okay. I know there's an exponent, right? E to the x, but if you just do u equals x, right? U equals that inside of the exponential function. U equals x won't change anything. All you'll be doing is switching the variables from x to u. Okay. So yeah, we could do that. Then du equals e to the x dx. And that's great. We have that e to the x dx on the outside there. So my integral becomes integral square root u du. Okay, so that's u to the half. So that's going to be u to the 3 halves times 2 thirds plus c. Okay. And we plug back in. So 2 thirds, u equals 1 plus e to the x, 3 halves plus c. If you guys do it the other way, very similar to previous problems, so I'm not going to show that. Um, let's see, let's get a good one here. Yeah, that's a good one. Let's try this one. 3 e to the x minus 2 squared. Yeah, so pause here. Forgot to say that. And try it. Okay. So yeah, inner function, right? So that's my guy. Du equals 3 e to the x dx, right? Taking the derivative and then putting a dx on there. Then we can divide by 3. Okay, now we have the e to the x dx. Plugging in, we just have, whoops, we just have u squared times 1/3 du. So that's a third. Okay, and then what's the integral or antiderivative of u squared? It's going to be 1/3 u cubed plus c. So that's going to be 1/9, not plus sign, excuse me. 1/9 u, so 3 e to the x minus 2 cubed plus c. Wonderful. Okay, let's do some definite integrals. Let's do some definite integrals. Let's I'll show you guys this one, then you can try the next one. Or you could try all of them if you want, of course. Um, Technically you should be able to do it. Okay. This is another one where you could use that strategy because this is a linear function of x, right? It's a -1 times x plus an extra 1. But yeah, so let's do substitution. U equals, hold on one second. U equals 1 minus x. Du equals negative dx, and then we can slide that negative to the other side. The bounds change, of course. So when x equals 1, 1 minus 1, so u equals 0. And when x equals 2, u is 1 minus 2, which is -1. So this integral becomes the integral 0 to -1. Again, those x bounds might seem backwards, right? But it's okay. In terms of evaluating, there's no difference. Um, and then what do we get? E to the u times negative du. Okay. So one thing we can do is to get rid of the negative. Remember what I said, when you have when you flip the bounds, you get a negative. But if we flip the bounds here, I'll have another negative, right? I have two negatives. Okay. So they cancel and I can ignore them. So that guy is gone and that guy is gone. Okay. So sometimes it's useful to switch back, right? Less negatives to deal with. But then we have e to the u evaluated 0, -1. So this is e to the 0 minus e to the -1. That's 1 minus 1 over e. Okay. Let me get you guys to try this one. You guys try integral 0 to 2 e to the 2x dx. Okay. So again, very similar. We'll do a u substitution. Okay. So that's what you should get. 1/2 e to the fourth minus 1, right? E to the 0 is 1. Okay, you pause here and take a look at it, right? Standard substitution one. Let's look at one that's a little gnarlier. So let's do integral 1 to 2 e to the 1 over x divided by x squared. Whoa. Okay, so don't get freaked out. The exact same strategy works here. Okay, the exact same strategy works here. So u is going to be our inside function. That's the 1 over x. Um, Let me just give you guys a heads up here. If uh your what do you call it, exponent is anything other than, a linear function of x, like a line, so like mx plus b. If it's anything other than that, 99.999% of the time, that's going to be your u sub. Okay. Um, I think it's 100%, but again, I don't want to be proven wrong with some crazy weird example. So I'll just say 99.999%. Okay. So that's x 1 over x. So that's x to the -1. When we do the derivative, we get negative x to the -2 dx, right? And I can move the negative over because I can see in my integral there's no negative. And then x to the -2 is 1 over x squared. Okay. And we have that. We have that. Okay. 1 over x squared. The x squared's in the denominator, right? You don't see the 1 over, but it's there. We also need the bounds. So when x equals 1, u is going to equal 1 over 1, which is also 1. And then x equals 2, u equals 1 over 2. Okay, so this is going to be integral from 1 to a half. And then e to the u. And there's no denominator anymore. It gets absorbed into the du. So it's actually e to the u times negative du. Okay, just like last time, we can use that negative to flip the bounds. Okay, so then this is e to the u. And then their bounds. So this is e minus square root e. Okay. All right. Logarithms. Okay. So let's talk about this. Um, that's weird. Why are they? One second. Okay. Sorry guys. I'm looking in the textbook here and they include here. Let's just write this up first and I'll talk about it. So integral 1 over x. Okay. So you might want to say natural log x plus c, but actually it's the absolute value. Okay. So, yeah, it's one of those things where usually we leave it off when we're being, you know, mostly correct and it doesn't really matter. Um, but it's just like when you do square root x squared, that's not x, that's absolute value x. Okay. So yeah, keep that in mind. So we'll erase that. So it's natural like absolute value of x. Okay, so in the textbook, they also include the integral of natural log x, but that's in order to get that solution, you have to use a strategy you learn in Calc 2. So I'm not sure why they included it because I'm not gonna make you memorize that. You're gonna learn how to evaluate that next term. Okay, so let's just do these. I will say this integral and the integral 1 over ax plus b. Very important integrals for Calc 2. Very important integrals for Calc 2. Give me 1 second here. Okay, yeah, and so in it's like I'm not sure how many, it's like in the middle of the term-ish, closer to the beginning, using something called partial fractions. These two are super important. There's one more that you learn next term, and those three kind of build your entire structure for how that works. So these are important. Um, what would this integral be? Well, I'm not sure. I mean, I know it's going to be something like a natural log, right? We're in the log section, but how are we going to get it? Well, the denominator is the inside part, so we can do u equals ax plus b, right? A and b are just numbers. So then du, what's the derivative of ax plus b? Well, right, you can imagine it like maybe 5x plus 7, right? What's the derivative of that? It's going to be 5. Okay, the derivative of this is just going to be a dx, and then we can divide by a on both sides. Okay, so this is the integral 1 over u times 1 over a du. So I can pull out that 1 over a, and it's just integral 1 over u. Okay, so that's 1 over a natural log absolute value of u plus c. And we can stick the ax plus b back in there. Okay, plus c. Now you don't have to memorize this, right? Doing a substitution on it will work every time, right? But these two integrals, like I said, are important for next class. So make sure you're solid on them. Make sure you write good notes on them, right? So you can look back on those. Um, but yeah, let's do it. So don't forget the absolute values, right? Again, doing that strategy of, because notice here, this is linear in terms of x. So you just divide by the derivative of that and do natural log of it, right? So that strategy at the end of last video works here as well, if you watched it. But let's try it. Okay, so let's try it. Let's do the integral 3 over x minus 10 dx. Okay, and then let's also do the integral 1 over x plus 2 dx. Go ahead and pause here. Okay, so doing this one, you should do u equals x minus 10. I'll leave the steps for you guys. The 3 just kind of hangs along for the right. It's 3 times this stuff, and you get natural log absolute value x minus 10 plus c. Similar thing here. You can do a substitution, which is x plus 2, and this will just be natural log absolute value x plus 2 plus c. Okay, cool. Now, this can be used for more than just, linear functions in the denominator. For example, something a little more complicated, um, something like this. 2x cubed plus 3x over 4x, or x to the 4, excuse me, and 3x squared dx. Wow. Okay. Well, trust your strategies, right? The denominator is, an inside function. It's one of those things that can pop up. So let's do w equals x to the fourth plus 3x squared. dw equals 4x cubed plus 6x. Oh no, 6x. Okay, that's not quite my numerator, which kind of sucks. But if you notice, it's off by a factor of 2. So if I divide by 2 on both sides, I do in fact get my numerator. Okay, and I can plug that in. So this is now the integral 1 over w times a half dw. So I can factor out the half. Integral 1 over w, natural log w, absolute value w, excuse me. And then we'll stick this back in. All right. Yeah, so for substitution, right, your denominator, if you have one, is probably a good inner function to use a substitution on. Something in parentheses, the exponent of an exponential function, right? Okay, those are kind of the three big ones. Okay, let's look at this last example and then we'll finish off today here. So 0 to pi over 2 sine x over 1 plus cosine x. Okay. Once you get the hang of this thing, you can almost try the u sub in your head, right? So what I'm thinking here is, okay, I'll do a u substitution. U equals 1 plus cosine x. Okay, what's my derivative of that? Derivative of 1 plus cosine x is negative sine x dx. And that's awesome, right? I have sine x dx, right? Remember, negatives or constant multiples don't matter. Um, so, that's if you get really good, if you can do it in your head. Um, but yeah, once you learn more strategies next term, that'll be more useful because you can do like a sort of process of elimination, like, oh, can I do U sub here? Oh, okay, can I do this other strategy here? Well, maybe not. Okay, right? And you just keep going like that. Okay, but you don't have to do that. The only strategy we know is U sub for this class, so let's just keep going. So we can do du derivative of cosine x, negative sine x dx, and then we can slide the negative to the other side. Awesome. Let's get our bounds as well. So when x equals 0, u equals 1 plus cosine of 0, so that's 2. Okay, and then x equals pi over 2, u equals 1 plus cosine pi over 2. Cosine pi over 2 is 0, so this is 1. Okay, so my integral is 2 to 1, and then it's going to be 1 over u times negative du. Again, we can use the negative to reverse the bounds. 1 over u. And then this is natural log absolute value u. And then my bounds. So this is going to be natural log 2 minus natural log 1. Okay, and we have to know this. Natural log 1 is 0. Any logarithm, you plug in 1, you get 0. So we get ln 2. All right, so that's about 0.692, I think. Okay. Yeah, so this is just more use substitution, but it's involving exponential functions and logarithms. Okay. Awesome. Thank you guys for watching.